think of a classification of a chemical signal two different ways, right? You can kind of think of it, number one, how do they get to their target? Okay. What's the mode of transport? Remember, there's a source, and then there's a target, and what determines the target is the fact that they have some receptor that can recognize that. How do they get there? If they travel through interstitial fluid, the mechanism is by diffusion, okay? And we would classify them as a paracrine if they're affecting an adjacent cell nearby, an autocrine if they're affecting themselves, which can happen, and a special case of a paracrine would be a neurotransmitter. This is a paracrine released by a neuron that either affects another neuron or it affects an effector, like a muscle cell or a gland. Okay? So that's one way, if they get there through interstitial fluid by diffusion. The other way is if they are absorbed by capillaries, blood capillaries, and they get transported by a pressure gradient, right? Blood pressure pushing things over long distance to their target. Okay? And if that's the way they're transported, they're a hormone. And I guess I should mention that, you know, hormones are we say that they're released or produced by endocrine glands. That's kind of, well, that's definitely true, but there are also just random cells in the bodies that can make hormones. There are cells that line the atrium of the heart that makes hormones. There are cells in the kidney that make hormones. There are also hormones that are produced by the hypothalamus in particular. And so if it is a hormone that is produced by a neuron, it would just be called a neurohormone. Right? So it's nothing different. It still has to get absorbed into blood plasma. It still has to get transported by blood plasma. But it's a neuron that's releasing it. And we'll talk about some of those as we move into the nervous system today and next week. So that's one way to classify them. The other way to classify them is based upon their chemistry. What is their chemistry? There are two very kind of opposite types of molecules with regard to chemistry and how they react with water. If they are water soluble, that must mean that they are polar. That must mean they're hydrophilic. If they are water insoluble, that's probably because they're mostly nonpolar, right? That makes them hydrophobic or lipophilic, right? They're soluble in lipids. Now, since regardless of what the chemical is that we're transporting, it's chemistry, it's being transported in water, right? Both of these are water. Interstitial fluid is water, blood plasma is water, so this chemistry is relevant here. Hydrophilic signals, whether they're a paracrine, autocrine, hormone, whatever, are water soluble. And so they will be just dissolved in the fluid. They're dissolved in blood plasma. They're soluble in interstitial fluid. Okay? Hydrophobic, on the other hand, are insoluble in water. Now, because of that, that brings some characteristics that we have to think about with how they'll work. We really focused on a lot of hydrophilic messengers the other day. Most chemical signals are hydrophilic, but there are a number that are hydrophobic. But the hydrophobic ones are pretty straightforward in their mechanism. For the hydrophilic, we know that since they can't pass through the barrier of the cell membrane, the receptors that are specific, right, for those signals must be on the surface of their targets. So the target cell would have to produce the receptor and insert the receptor in its cell membrane. And it can regulate the amount of receptors in the cell membrane, right? It can upregulate, put more of them there, downregulate less of them. But the cell is in control over putting the receptors in the membrane. On the other hand, hydrophobic signals, there would be no reason to have the receptor on the surface because these compounds can pass very easily through the cell membrane. So because they pass very easily through the cell membrane, those receptors are now going to be cytoplasmic, we would say, or even nuclear, right? They could either be in just the cytoplasm or in the nucleus. Many of them are in the nucleus. Now, having said that, there are exceptions to this rule. There are some receptors for hydrophobic signals that are on the cell surface, but they're rare. Okay, so we like to think of generalizations. So while there are exceptions to that, there are no exceptions to the hydrophilic one. None of those can go in, so they all have to be on the outside. what's interesting about this chemistry is that because these hydrophilic ones are water soluble, they're just transported dissolved. I mean, just think if you wanted to transport sodium chloride around, you put sodium chloride in your water, it dissolves, right? So it becomes, if you want to think of it, part of the water, part of the solution. So it's not a problem transporting it around because it's dissolved. Anything that's not soluble, all of these hydrophobic compounds, right, it would be like transporting around a little fat droplet inside of your interstitial fluid, inside of your blood. And you know that can't work, right? So the way you have to transport it is by tricking the water into thinking that it's hydrophilic. And how do we do that? We do it by masking its hydrophobic properties by carrying it bound to a carrier protein. So for example, testosterone is a steroid-based hormone that has to get transported around in the body, right? It can't be just as testosterone, so it gets carried bound to a protein. And the protein's called androgen-binding protein, and that's what transports it. Now this creates another level of kind of regulation because testosterone won't work because you can't transport it unless you also produce the carriers. To give you an example, you've heard of good cholesterol and bad cholesterol, right? Cholesterol is hydrophobic. It's not a signal molecule as such this way, but it does have to get carried in the blood, in blood plasma. But it's not soluble in plasma, so we carry it bound to a protein. So HDLs and LDLs, HDLs are considered good cholesterol. It's not the cholesterol that's good, it's the carrier that's good. Because of its structure, it's less likely to form plaque. Because of the LDLs, the protein carrier structure, it's more likely to form plaque. And we'll talk about some of that when we do the cardiovascular system. But again, you need those to carry cholesterol. Okay? So hydrophobic things, when they're being transported, they have to be bound to a carrier, a protein carrier. And that's just to help its chemistry. Because these hydrophilic things bind to cell surface receptors, in order for something to happen inside the cell, that receptor has to be linked to some transduction pathway or something, right? It's either going to be linked to an ion channel, channels open and close. It's going to be linked to an enzyme that gets turned on or turned off. But most of them trigger these second messenger systems, right? This cascade of a transduction pathway that